Okay, we are now recording. Let me get the PowerPoint open from current slide. And this is where we'll be beginning today. But before we do, I have at least one fairly major announcement. Okay, I think I told y'all last Monday, but since this class is the first one of the week, and I don't know if they had come up with this idea yet or not, and since we didn't meet on Wednesday, in fact, no, they hadn't come up with this idea yet. That's right. It was Tuesday, right before the beginning of my first class. I mean, like within 5 minutes of the beginning of my first class, I got a call from my boss about what the plans were. And so you may have heard it in another class, but you haven't heard it in this one. Okay, and here's what it is. Evidently, enrollment for spring term is pretty low right now. Okay, and so I think the administration's sort of panicking a little bit because enrollment's low. So somebody decided that they're going to have this week that we're in right now, Monday through Thursday, as a big push for advising and enrollment for spring term. Such a big push. At one point, I heard they wanted all faculty members on campus all 4 days this week, Monday through Thursday, where there's no classes on campus except hybrids, and none of those are the academic ones. But they didn't want people who had, health issues, so I'm not going to be there, obviously. Then I think they backed off and just said, fulfill your hours. But anyway, they're running information tables and advising tables and registration tables on the Birmingham West campus in that new Academic Success Center, that big building there on Wilson Road that basically is sitting just about where Winona Elementary School used to sit. When Winona built a new elementary school, they tore down this one and gave it to it belonged to the city, so the city deeded it or whatever they do to give it to the college, and that's where they built the Academic Success Center. Now there's obviously somewhere in that building, it's a big building, and I don't know what all's in there, but there's somewhere, some really big room somewhere that they're going to have the advising set up. They've got tables set up for various places, career tech, nursing program, pre-nursing program, general studies, and possibly some others. I don't remember all what ones are there. And they're going to have either faculty, staff, or administrators at every table from 9 o'clock this morning, 9 till 7 every day this week. Monday through Thursday, not Friday, but Monday through Thursday. And that's why they had a big push for all faculty to be on campus this week, even though there's no classes on campus. They're to do the recordings from campus. They're to, stuff. It's kind of crazy. Now, I want to ask you, the four of you, are all four of you coming back for spring term? Yay or nay? Okay. Have you already registered for spring term? Not yet. Okay. That's all four of you, not yet? Okay. All right. Then now, here's your options. Okay. You can sign up. And here's what my perspective is. I don't know if this is correct or not, but I know that last summer, before fall term began, they had such a huge push on virtual advising, and I was signed up for something like 6 or 7 hours a week to do virtual advising, and most weeks, the vast majority of those half-hour time slots for 6 or 7 hours, so that was 12 to 14 time slots, were filled. And now, not always did the students show up. They sometimes canceled. And there's occasionally they didn't even, no one signed up for that time. But for the first several weeks, I never missed a 30-minute advising slot. There were always students there. Now, have y'all heard much about virtual advising this spring, this fall? Yay or nay? You have? Okay. Um, I just, I've been signed up for at least 5 hours a week, every week this fall. And how many have I had? Zero. Where in the world is my Zoom thing? Let me back off a moment here. Okay, I just realized I wasn't seeing any of you. Not that I usually do, but let's get started with 86. Okay, I just realized this wasn't, I didn't have everything set up right because I was saying, I can't see you guys, or at least your names. Okay, let's get the new share set up for 86. And now it's not even showing me 86. This thing, I like Zoom pretty much, but it has some weird. Okay, let me go back and try to share again. There we go. All right. Now, but what I was saying, so far, this fall, I've been signed up for at least 5 hours virtual advising every week, and we're in what, week 14 right now. You know how many advisees I've had contact me through the virtual advising center? Zero. Zero. Okay. Now I've advised students who I've had before, that they've contacted me and let me know, ask me questions, emails. I think I've had a few on the phone and stuff like this. So I've been advising students, but they haven't come through the virtual advising center, and I do not know why. I don't know if their scheduling thing isn't set up, but it was just almost full in the summer and completely empty in the fall. So I don't know. Did any of you try to do virtual advising, or you just had put it off until now?
I did it for this term,
Uh-huh.
but what he said, I have Mr. Holloway, and he doesn't help me much because I already know what to do.
Uh-huh.
So all he did was check my classes and just gave me the go for yes or no.
Okay. Uh, yeah, and actually Mr. Holloway called me this morning because they had him down for 2 tables and there were some conflicts there. So, but I couldn't do anything about it. I passed him on to Dr. Pruitt to do that. So yeah. So here's what your options are for this week. If you want to go to campus and participate in the sort of face-to-face virtual advising, number one, be sure you bring your mask and wear a mask. You cannot get into a building without your mask. Oh, I was telling you where the virtual advising was going to be. On the Birmingham campus in that new Academic Success Center on Wilson Road where Winona Elementary used to be. On the Bessemer campus, it's in the Ethel Hall Auditorium. Now, or if you're familiar with the Bessemer campus, when you come in, there's 2 gates that you could come in, both off the Bessemer Superhighway. The one closest to Bessemer, at the light where the hospital is, if you come in that one, you have to go around the A building and circle all the way around it, and then you'll see the big parking lot down there at the on the just before you go out the next thing. You'll see the big parking lot there. The big building on your right is Ethel Hall, and you'll see the name of it on there. And what you best way is to walk around to the back side and come in. Then you'll be on the right level when you come in through the glass doors. Ethel Hall Auditorium will be just on the left. Okay. If you do go in through the parking lot level, you have to find stairs and go upstairs and then find the wander around through the hall. So it's a lot easier to find if you go uh, uh, from the parking lot, go up the little road that goes up the side, and come in that way. That's sort of the main entrance. When you come in, the auditorium just on the left. If you see the counter on the right, they'll point you right back to the left and get you in the auditorium. Okay, so you have two options. What I would say to do, the safest thing would be to sign up for virtual advising, because we are still doing virtual advising. Sign up for that, get whatever help you need, and then go on and register. Guess what? We, the faculty members, we, the administrators, we, the staff at the college, we can't register you for classes anymore. In the old system, we could. In the new system, all we can do is advise you and help you get registered, but we cannot do it. You have to register yourself. I think you probably remember that from the summer when you were registering for fall. That system is still in place. So that would be, in my mind, the safest thing to do. You don't have to go to campus to do it. You don't have to be exposed. But if you want that one-on-one, the tables are going to be set up with plexiglass between the advisor and the advisee. Everybody will be masked, and you will be social distanced and all like that. So there may be some waiting, or there may not be. I don't know. I don't know how students are going to be responding. But I would say, if you can, sign up in the Virtual Advising Center, get with an advisor, get checked off for what you, make sure you know what you need, and then register yourself. But if you don't know how to register yourself and you do need that additional help, go to either the Bessemer or Birmingham campus anytime between 9 in the morning and 7 in the evening, today, tomorrow, Wednesday and Thursday. Okay, so get that done today, so the administrators can quit panicking and coming up with some of these crazy ideas. Okay, any questions? You can tell I'm not a big fan of.
I was just asking for future reference. Do you teach Cal 3 and linear algebra, or you just teach Cal 3?
I used to teach them all, but this is my last term. I'll be retiring on the 1st of February.
Oh, no.
Oh, yes, yes. Sorry about that. Yeah. Uh, if you are looking for me on the schedule, you will not see me on the schedule because I am retiring. I'm 69 right now. In January, I'll turn 70. That's enough. I need to move on and let someone fresh blood come in and take care of things. And uh, the more this term has moved on, the more convinced I am the time is right for this. I love teaching, but my treatments, the disease, everything just seems to have stepped it up a notch this time. And so, and then I prefer being in the classroom, but I can't be in the classroom because of my health issues. And I like virtual, okay, but I really like to interact with students. I like to read your expressions. I like to know when I lose you and when I don't. And then they piled on top of everything else all this stupid stuff we have to do with Blackboard now. Do any of you look at the weekly overview and all that kind of stuff before you do class each week? Okay. Yeah. I I I don't think that many students do. Perhaps if a instructor is teaching strictly through Blackboard and letting Blackboard do the teaching for them, I guess you have to. Online classes, you have to. But these virtual classes, they make me do. I mean, basically, um, if I were on the ball, I'd probably have it done earlier. But the Sunday afternoon and evening, I'm spending hours setting up those things for today's classes. And I've already started this morning setting up the ones for tomorrow classes. And I don't think students ever look at them, or very seldom look at them. So this kind of stuff. So I guess I'm old and stuck in my ways, and I find it totally ludicrous to pile all this on. That's why I'm behind in grading right now, because most of my office hours are spent with the Blackboard stuff, and it's just totally useless, but we are required to do it. So anyway, that's enough of my singing bad, sad song. So let's go on and get to algebra. I mean calculus, okay? If I can get the slide to open. Okay, we're in 8.6. Well, let's see, let's back up one slide. We're in Chapter 8. Chapter 8, Integration Techniques and Improper Integrals. We're on our, I think, next to the last technique, you might say, and this is numerical integration. The last one is using tables. I would have reversed the order of those, but they did it this way. Okay, so numerical integration, and what our objectives here are to approximate a definite integral using the trapezoidal rule. And a lot of texts I've taught from before would then also have in here approximate a definite integral using the midpoint rule. This book does not do but just a slight mention of the midpoint rule. We've done it a little bit in other contexts, but they move right into approximate a definite integral using Simpson's rule, which is, frankly, the only one you really need, because that's the best one, okay? And then it's analyze the approximate errors in the trapezoid rule and the Simpson's rule. So that's what we're going to be doing today. And we'll start with the trapezoid rule, which is okay, but actually the Simpson's rule, so much better. People very seldom use trapezoid rule anymore, but it's pretty easy, okay, relatively easy. Okay, I'll put it that way. All right, some elementary functions do not have antiderivatives that are also elementary functions. Well, that's a problem. That means you can't integrate them. If they don't have an antiderivative, that's an elementary function. For example, there's no elementary function that has any of the following functions as its derivative. The cube root of x times the square root of 1 minus x. Those are both perfectly good elementary functions, but there's no way you can do an antiderivative and find, that there is no other function that has this as its derivative. Square root of x times cosine x. Not going to happen. Integration by parts, nothing is going to work to get you out of that one. Cosine x over x, okay? No way, okay? Even something as simple as the square root of 1 minus x cubed. If that was a 1 minus x squared, yeah, there's a trig substitution. But there's not anything that will give you that as a derivative. Okay, and something as simple as sine of x squared. You cannot integrate this with any technique that we've done so far. Okay, now, also in real life, situations like that, hey, you can come up with some really strange functions, and you may not know any. There may actually be an integration technique, but it's going to be really hard to find, okay, and figure it out. So a lot of times people will just use numerical integration. It seems sort of crazy, but you spend all this time learning to integrate, and then people buy packages and do the integrations by the numbers, you might say, numerical integration. If you need to evaluate a definite integral involving a function whose antiderivative cannot be found, then the fundamental theorem of calculus is still true. It cannot easily be applied, so in this case it's easier to resort to an approximation technique, and these techniques can be very good. Okay, one way to approximate a definite integral is to use trapezoids, okay, as illustrated here. In the development of this method, it's assumed that f is a continuous function, this curve here, f, assume it's continuous. That's usually the case, okay? And positive on the interval that you're dealing with. From A to B, this function is strictly positive, okay? Now, if you're trying to do the integral from A to B of f of x dx, and this is one of those functions that does not have an antiderivative, okay, that is an elementary function, what can you do? Well, you do what we always do, okay? Split it into, or what we did when we were developing how to integrate. Split it into a partition. They show here x of 0, x of 1, x of 2, x of 3, x of 4, and that is your b. X of 0 is your a, x of 4 is your b. Split it into that, and then draw little trapezoids to represent the area under that curve. Now this one overshoots just a little bit. This one overshoots a little bit more. This one undershoots just a little bit, and it's hard to see what this one's doing. I think it's pretty much undershooting just a very, very small amount. Okay? Well, we know the area of a trapezoid. I don't know if you remember the area of a trapezoid, but you've had it before sometime in the past. It's the width of this little, what would have been a, well, let me put it this way. I want you to visualize this for a moment. Let's take this trapezoid here, flop it over itself. Okay, now what I mean by that is reverse it this way, and then put this upper point here down here on the lower point here, put this lower point here on the upper point there, and let this end stick up in the air. Okay, I'm going to try to draw that, but my drawings, these ionizing pens, this pad, not particularly good, but let me do my best to try to draw it, if I can even find the pen. There it is. Okay, so I'm going to flip this over. This is supposed to be a straight line. Okay, now that's not quite high enough, is it? Something like that. In other words, take this and flip it over this way, okay? And this area here then would be the same as that area, right? Well, what does that make? If my drawing were any good, that would make a rectangle. What's the length of that rectangle, or the width of the rectangle? Delta x, x1 minus x0. What's the height of that rectangle? It's, let's call this f of x0, or f of a, plus f of x1. So it's the sum of this side and that side, because this side flipped to here and this side flipped to there. Okay, and you have a rectangle. So if you do that for all of them, then you have an area that's exactly twice the, well, of the approximate area under that curve. Okay, so that's how we do that. That represents the area of the region bounded by the graph and the x-axis from x equal a to x equal b. Okay, okay, I'm sorry. Yeah, those are the trapezoids. I thought they may have, I don't see the word trapezoid in there, but that's the approximate value. Okay, so first partition the interval a to b into n subintervals. That's exactly what we had back there. That n was 4. Okay, each of width delta x, which is b minus a over n. Okay, let's go back here and see. Whatever the length here is, where in the world, there's my pen, b minus a, that would give you the length of this rectangle, the length of this shaded portion. B minus a is the length of that, divided by 4 gives you each of these intervals here, the length of each one of those. Okay, so there's your delta x. A is the first x of 0, then x of 1, then x of 2, x of 3, x of 4, all the way up to x of n, and that'll be your b of n. Then form a trapezoid for each subinterval. okay? And the area of the trapezoid, just like we said, would be the F value, or the Y value, the height of this, the sum of the height of x sub I minus 1, that's the short side on this one, plus the long side on this one, divided by 2, because when you add the long side here to this one and the short side here to that one, you have twice the area. That gives you the rectangle. We want just the area of the trapezoid, so you take half of it and then multiply it by the width. So this will be half the height of the rectangle, the area of the rectangle, plus times the width of the rectangle. So that's the area of the ith trapezoid. Okay? Now, you do those areas throughout A to B, wherever that is, and add them together. Now, of course, they're not going to give you the exact answer. This is an approximate answer. And what's this way to make a better answer? Make your interval smaller. Increase your n. Of course, that means you're going to be doing more of these values, but your computer can do that, and they do have them doing it. We're going to do them by hand, but this is something that can be done by a computer. Okay, this area here is what shows up down here too, but that box sometimes covers it. Okay, so let's move on. This implies that the sum of the areas of the n trapezoids, okay, which would be, now every one of them has the same width, b minus a over n, okay, same one. And every one of those trapezoids you're dividing by 2. So let's take the 2 out and put it with the n. They're both in the denominators and have them there. So then what do you have? For that first trapezoid, you have f of x0 plus f of x1. For the next trapezoid, it's f of x1 plus f of x2. The next trapezoid is f of x2 plus f of x3. F of x3 plus f of x4, and so on until that very last one, you get f of x sub n minus 1 plus f of x sub n. Okay, now you had 2 of these, but you only have 1 of those and 1 of those. You have 2f of x1, 2f of x2, 2f, all the way up to, except for the first and the last, you have them twice. Okay, so therefore, you just have 1 f of x1, 2 f's of x1, 1 f of x0, 2 f's of x1, 2 f's of x2, 2 f's of x sub n minus 1, and then just 1 f of x sub n. Okay, probably not getting all my subs said properly, but I hope you're following what I'm doing. So what does that give us? By letting your delta x be that b minus a over n, you can take the limit as n goes to infinity to obtain this is the limit. Okay, there was that term out in front. These were all those other terms that were left over, and the limit of that, let's pull out all the things that don't have n associated with them. Okay, well, this one, remember, was your f of a. This one over here was your f of b, and that's divided by 2 times delta x. Okay, your delta x is b minus a over n. Okay, so you have the 2 here, and that would involve the n. Yuck. Now, all the rest of those have this 2 here is going to cancel out all the other 2's. You took care of this one and this one with this part of the sum. The rest of these are just the sum from I equal 1 to n, okay, of delta x of I. Now that doesn't quite seem right. I can see where the f sub 0 is taken care of here. That would include an f sub n here, which isn't quite right, because you've already taken care of the f sub n. So this should be n minus 1, I think, or this should be n minus 1. Okay, but they're just off a little bit there. Okay, so here's your limit as n approaches infinity of f sub a minus f sub b over, and this is your delta x is b minus a over 2n. Okay, now here you got the n back in here again. So I don't see why they keep going back and forth on that, but they do. And then this is the limit. Then it's all they've done is take the limit inside here and inside here, and this would give you this one. Okay. Now, here's the surprising thing. They say as the limit as n approaches infinity, your b minus a is going to 0. And if that's going to 0, then that first term is going to 0. And the limit of this term is simply your integral from a to b of f of x dx. Okay. Okay. But that we can't do anyway. Remember, we can't integrate the f of x. That's what we started with, but we couldn't integrate it. But what this is showing you in a long roundabout way is that that approximation, as you let that n goes to infinity, so your delta x is getting smaller and smaller and smaller, this does give you the right answer. Now, can you do summations infinitely? No, you can't, but you can get them down to the design or accepted limits of correctness. Okay, we'll talk about that in a minute. So that result is summarized here, the trapezoid rule. Let f be continuous on a to b, remember that's a requirement. They also said that it has to be positive. They didn't mention that here, but the trapezoid rule for approximating this integral, which is the one we wound up with before, is approximately, it's not equal to, b minus a over 2n, that's your delta x, then your f sub x0 plus 2f sub x1 plus 2x f sub x2 plus 2 f of x3 all the way up to 2 f of x sub n minus 1 plus f of x sub n. Okay? Now, as n approaches infinity, this right-hand side also approaches the left-hand side. Now, you know you can't approximate infinitely, but you can get as close as you want in accuracy. It's just like we said when we started off integration, if you remember, whenever that was, it was the method of exhaustion. You just keep doing it until you finish. Okay? So, until you get close enough. That's all you want. So here's example 1, and this is on page 560, just below that theorem that we just had up there. Use the trapezoid rule to approximate the definite integral from 0 to pi of sine of x dx. Now, time out a moment here. We know what this integral is. We know exactly what it is. This is not one of those that we don't know how to integrate. But we're going to practice on this one, and then we will see how good we get. Okay? And we're going to compare the trapezoid rule when n is equal to 4 intervals and when n is equal to 8 intervals, as shown here. Okay? So when we split from 0 to pi into 4 equal intervals, our delta x is going to be pi minus 0, that's pi, divided by 4. Okay, so each of these is pi fourths. 0, pi fourths, pi halves, 3/4 pi, and pi. Okay, now we see what those trapezoids are here, and what we need to know is the value here. F of 0 is 0. F of pi fourths is, hopefully you remember that, the sine of pi fourths is square root of 2 over 2. F of pi halves is 1. F of 3/4 pi my writing isn't too good, is square root of 2 over 2 again. And f of pi is 0 again. Okay. Now, what we're to do here, our estimation using the trapezoid rule was, if you remember, let me flip back just so you'll see. Here we go. It's b minus a, that is pi, divided by 2n. Well, your n was 4 in this case, so that's 8. So that's what's out front. And then you do your f of x0 once, 2f of x1, 2f of x2, 2f of x3, and then to 1f of x4. Okay? So let's do that. The summation, I don't know where to write it. There it goes. Let's do it right here. Would be b minus a, pi minus 0, divided by 8. So that would be pi eighths times, okay, f of x0 is 0, plus 2 times root 2 over 2. So that's just root 2. Okay, plus 2 times 1 is 2, plus root 2 again. 2 times root 2 over 2 is root 2, plus 0 again. Okay, so this is going to give us pi eighths times 2 root 2 plus 2 over nothing. I'm sorry about that. Okay, the zeros don't add anything. 8 will go into these two 2's 4 times. So what we get as an answer is pi fourths times root 2 plus 1. Okay, now I'm going to pull up my handy dandy calculator, which is my phone. Okay, I think it should be fully charged now. It is. Okay. And there's my calculator mode. And I've got to turn it sideways to get it to scientific thing, and that's going to be pi, I have a pi key there, divided by 4 times, I'm going to open parentheses and do a root 2. I have to enter the 2 first and then do a square root, plus 1, close parentheses, equal. I get 1.9 basically, approximately 1.9. Now, do you want to go on and do the other one? We could. I'm real tempted to tell you the exact answer now, but I guess I'll resist temptation for right now and go on and let's do this part. Now, again, our f of 0 is 0, is equal to 0. And these were the same. This was root 2 over 2. This is root 2 over 2. Okay. The pi eighths, we're going to have to calculate that. And it's okay. I mean, it's just sort of a pain in the neck. And 3/8 pi, we're going to have to calculate that. Pi halves is still 1. This one over here is still 0. But the good news is these two are the same, and these two are the same, just like we found these two being the same and these two being the same. Okay, so we really only have to calculate these once. The f of pi eighths and 3/8 pi, we're going to double those. Okay, so our summation, the approximation, is going to be pi minus 0, that's pi, divided by 8, because our n now is 8, and it's 2n. Remember, that's the rule. They pulled the 2 out there. So that gave us 16. So we get pi 16ths. I'm going to write it down here, just like I did this one. Pi 16ths times 0 twice, and then this was square root of 2 over 2, but it's twice that. I'm sorry, okay. We got to do our pi eighths, okay? So let's go on and get that done. Okay. Got to get it. Yeah, there we go. To get a sine function, we need to do pi divided by 8 equal, I get about 0.4, okay, and then do the sine of that, and that gives me about 0.38. I want to do a little more precise than that, but what we're going to do, remember, is double that. So we will take this times 2, okay, and that again isn't going to give me anything real easy to do. About 0.765, wow, there's just no good round off place. 0.765367. Okay, let's do it that way. Let's do this one to be, where is my cursor? There it is. Okay. All right. This is 2 times this. I'm just going to say that is going to be 0.76, 0.765367. Okay. We'll just keep that in mind. The 2 because you have 1 over here and 1 over here. Okay. So that's going to be 0.765367. Okay, that's going to be that second point. Okay, so this is going to be a plus here. Okay, and then the next one was our root 2, but we have 2 of those. So remember that was 2 root 2. So this is plus 2 root 2, and that covers both this one and that one. Okay, and then this one, the 3/8 pi. 3 times pi divided by 8 equal 1.17. I want to take the sine of that. That's 0.923 blah 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 blah. I'm going to multiply that by 2 because we've got 2 of them also, and that gives me 1.84776. So this, the 2 of these is going to be 1.84776. So that would be plus that 1.84776. Okay, so that gives me this twice 0 is 0, twice this one is that one, twice that value is that one, I'm sorry. Yeah, just like it was here. And then twice this one is that one. And then we got twice, we don't have twice one. We only have one because there's not two of those. So then we have a plus one. Okay. Now, since I've got this one on the screen, I'm going to add to that. This is tedious, I agree. Okay. The 0.76537 plus, I'm going to go on and do the 2 root 2, 2 times 2 square root plus 1. Okay, and then I'm going to multiply that by pi and divide it by 16. And I did something wrong. No, okay. Yeah, I definitely did something wrong. Okay. Now, I can't see my error right now, but it's, let me try that one more time. I've got 0.76537. Okay, I'm going to clear all this. 0.76537 plus 2 times square root of 2 plus 1.84776 plus 1 equal. Okay, I'm going to multiply that by pi and divide that by 16. And I still get the wrong answer. I don't know where I made my dumb mistake, but I must have made it somewhere. We did twice that, twice this. Is that just a root 2? I think that's where my mistake is. Oh, wait. Sorry about this. I'm just doing, okay. We got one of these. We got twice this one, but then twice that twice, okay? We got one here and one there, but we got two of these, two of these, two of the, okay, I'm sorry. I forgot that I was doubling each of the things in here. I just doubled it because of the added twice, but I have to double it again. So let's start back over there, and we'll do the 0.76. Sorry about this. Okay. The 0.7653 5367. Okay, I'm going to double that one. I should have done that ahead of time. Plus, and I've already doubled this one, 2 times root 2 plus 2 times 184, 2 times 1.84776 plus, And this one we double 2 plus the 1 plus 2 equal, and multiply that by pi, and divide that by 16, and we get 1.97, which that rounds to approximately 2. I'll keep the 1.97. 1.97. This one was something less than 1.9. This is 1.97. Now let's do the actual integral. Sorry that took too long. The integral of sine x would be minus cosine x, okay, right, evaluated between 0 and pi. Well, that would be minus cosine pi minus a minus, which is plus cosine of 0. Well, cosine pi is minus 1. Negate that, you get a plus 1, and cosine of 0 is 1. 1 plus 1 is 2, and this is exactly 2. So done 4 times. Okay, let me see if my dog's barking. I don't know what that means. It may be the person's here. So hold on just a minute. I'm going to pause the recording just for a moment and see what door. She barked. They left. So I went around. I was just going to check and see if they were here. There was no sign they had shown up, and the phone hadn't rang anyway. So anyway, sorry about the fake. But anyway, so you see the trapezoid rule in just 4 steps gave you a pretty good approximation. The actual value is 2. In 8 steps gave you a very good approximation, 1.97, which basically I would have come close to rounding to a 2. In fact, I said I would, but you get a computer to do this, and this is really easy. All it has to do is compute these once, and then compute another set there, double them if it does it correctly, unlike what I was doing, and then you come up with a very good answer in very few steps. So the trapezoid rule does a good approximation of that. Let's see how the book does it. I think I can just scroll past this. If I can scroll past this. Okay. So when n is equal to 4, your delta x is pi divided by 4. Pi was the difference between the last value, pi minus 0. That was your pi divided by 4. And you obtain that this thing would be approximately pi eighths. Remember, it was b minus a over 2n. That's your pi over eighths, times the sine of 0 plus 2 times the sine of pi fourths plus 2 times the sine of pi halves plus 2 times the sine of 3/4 pi plus 1 times the sine of 0. Not sine of pi, which is 0, is what I was trying to say. Okay, so this will be our pi eighths here times the sine of 0 is 0, twice the sine of pi fourths. Sine of pi fourths is root 2 over 2. Twice that would just be root 2, plus 2 times 1 is 2, plus 2 times sine of 3/4 pi. That's the same value as this one, root 2. And then sine of 0 is 0 again, same value as that one. So what do we have? Pi eighths times 2 root 2 plus 2. Factor out the 2 and divide out that, and you get pi over 4 times 1 plus root 2, which is exactly what we got, and that comes out being 1.896. So I had rounded to 1.9, but it was a little short of 1.9. So not a bad approximation, but not quite there. Okay, but when you just go up to 8, twice as many intervals, you get much better approximations of that. This would be about pi over 16. Again, the b minus a, which is pi again, divided by 8. that is your n, but your rule says over 2n, so that gives you 16. There's your sine of 0 and your sine of pi again. You know they're not going to give you anything. Twice the sine of pi eighths, which that's not one I know off the top of my head. Twice the sine of pi fourths, that's one I do know off the top of my head. Twice the sine of 3/8 pi, which I don't know. Twice the sine of pi halves, which I know. And the 5/8 pi is going to be the same as 3/8 pi. And the twice the sine of 3/4 pi is going to be the same as that one. And this one's going to be the same as that one. And then your sine of pi is the same as that, which is 0. And when you add those together, and they've left off the zeros at the ends now, pi 16ths times, and they've combined lots of things now, okay, the 2 times pi sine of pi halves, that's where the 2 came from. The 2 times root 2 over 2, that's where the sine of pi fourths, they've sort of mixed these up. This one plus that one gives you 2 times that, just like we had before. And now we get 4 times the sine of pi eighths, because it's twice here and twice there, okay, plus 4 times the sine of 3/8 pi, okay, twice from here and twice from there, okay. Now, if you factored out the 2 here, okay, and that gave you pi eighths, that would leave you a 1 there, a 1 there, a 2 here, and a 2 there. And I think that's what they do next. No, they don't. They just go straight to the answer at 1.974. Okay, and if you're going to 3 significant digits, 1.97 to me would be an okay answer. It's not exactly 2, but you know, if you went from 1.86 or whatever the last one was, with 4 steps, and 1.974 and 8 steps, if you went to 16 steps, and you know you already have all these things calculated for you, you would just put in a pi 16ths twice, a 3/16 pi twice, sine of 3/16 pi twice, and you know, you just do that, and it's a pretty easy thing to program, okay, and you'll get a really good approximation then. For this particular integral, you could have found the antiderivative, determined the exact, I think that says value of the region is 2, and that was pretty close to 2. So trapezoid rule gives you pretty good. It's the exact area of the region is 2. Now, we move now to Simpson's rule, okay? Now, Simpson's rule is a little more involved, okay? That's putting it sort of mildly, but it's much, much, much more accurate, okay? One way to view the trapezoid approximation of a definite integral is to say that on each subinterval, you approximate f by a first degree polynomial, a straight line. In Simpson's rule, you take this procedure one step further and approximate f by a second degree polynomial, which is by a parabola. Rather than a straight line, you're going to make an arc that hopefully fits the curve better than the straight line did. So before presenting Simpson's rule, let's consider the following theorem for evaluating integrals of polynomial degree 2 or less. Okay, so here's an integral of this polynomial function ax squared plus bx plus c. If that's your polynomial, then the integral from a to b of that polynomial, okay, now where in the world does this come from? I know where they're heading with it, but how can they give you this right here? Okay, I think what we in order to see where this is coming from, we need to actually do that. Let's take the integral of, I can't get my pen to show up here. There it is. Okay. The integral of ax squared plus bx plus c dx. Okay. That's what we're doing, plugging that in here. And this will be a x cubed over 3 plus b x squared over 2 plus cx. Okay? And we're going from A to B. Okay. Now, all right. This is going to be, and this is probably almost a waste of time, but let's do it. Okay. A times b cubed over 3 plus b, capital B, times little b squared over 2 plus c times little b minus a times little a cubed over 3 minus b times little a squared over 2 plus, minus c times a, little a. All right. Now, oh boy. What we're going to pull out of this is P of A. That's going to be the first thing we're going to pull out of it. Okay? That would be capital A little a squared plus capital B little a plus C. Okay? This is P of A. Okay? P of B would be capital A times little b squared plus capital B times little b plus capital C. Okay, so we've got these two. Now, this seems like such a pain in the neck to do. And maybe they don't want us to do it. They just want us to take their word for it. But it is the case. Okay. We have to also do the polynomial here of half of a plus b. So P of a plus b over 2, the average of a and b, would be a times a plus b over 2 squared plus b times a plus 2 over a plus b over 2 plus c. Okay, that would be what this is. Now 4 times that would be a 4 here, a 4 here, and a 4 there. Okay, now we've got some work to do here. A plus, if I could find my pen again. There it is. Okay. A plus B squared. Okay, I'm going to write this down. 4 times A times A squared plus 2AB plus B squared over 4. Okay. Plus 4 times B, capital B, times A plus B over 2 plus 4C. Okay, that's this thing here. Okay, is that one up there? Boy, what a pain in the neck this is. Okay, so if you add those together, okay, here was your P of A. This is A squared plus capital B A plus capital C plus, and then 4 times these, that's the one I've got here. This is 4 capital A squared plus 2AB plus B squared. Okay, and I meant to do on and do this, so let's divide out the 4 there. So that 4 is no longer there. Okay, plus, now I'm going to erase that because I've already done that. So that's, this part is gone because that's what I wrote there. Let me get my pen back. Okay, and here the 2 will go into 4 twice, so you get plus 2B times A plus B plus 4C. Okay, now I've taken care of those terms, so I'm going to erase those. Okay, all right, and then the P of B was this one down here. That's another plus A B squared plus capital B little b plus C. Okay, now all that times B minus A over 6. Okay, how can this be? Let's do like terms here. Here we have a 4A squared, I'm sorry, capital A little a squared, and here we have another capital A little a squared. So that's 2 of them. You know what? They didn't prove their integral, and I don't know why I'm wasting all this time to show this. But it says observe the coefficients in the trapezoid rule have the pattern 1 2 2 2 2 2 2 2 to 1. Okay. No, I'm sorry, I'm looking at the wrong page here. They do the proof here, and they start it the same way we did, except I forgot to do I forgot to do my minus b's, didn't I? Shucks. Okay. I started off okay down here, but I didn't plug these values in. No wonder it was coming out wrong, weirdly. I needed to plug in the B's first and then subtract them when I plugged in the A's. I thought I had done that, but I think I must. Oh, there is where I did it. Okay, there I did that one. And then when I went up to do I didn't do the one for, okay, no, I had done this. Okay, that's what this becomes. Okay, now if you had started doing this, you see there is, well, well, they did it a lot smarter than I did. Okay, they first noted this. You have this minus that. So that's a over 3. So I'm going to erase these middle ones here. Hopefully I won't need them again. Okay. We could have gotten there the way I was going, but it was going to be a long and nasty journey. So let's do it this way. Okay. This minus that. Certainly the a comes out. Okay. And a over 3 comes out. Okay. And then you're left with the b cubed minus a cubed. Well, if you remember that, that's a b minus a times b squared plus ab plus a squared. I don't know if you remember that, but you can factor a cubed minus b cubed into a minus b times a squared plus ab plus a squared. B squared plus ab plus a. Okay. Now, this next term here, okay, the b over 2 factors out, capital B over 2, and what you're left is a squared minus b squared minus a squared, which is b minus a times b plus a. Okay, conjugates. Okay, and then the last term, certainly the c's can factor out. That's going to be a plus, and then you're left with b minus a. This is how I should have done it. This mess at the top is a pain in the neck. So if I can get my eraser to show up, which it doesn't want to do, here we go. I'm going to erase all this. I was coming at it the other way. Let's go at it the better way, perhaps. We'll see. I may have to go back and do all that again. If so, I'll leave that to the student. Okay. All right. So what do we have now? B minus a, you see, shows up in every term. So let's factor that out. B minus a. Okay. Now, if you factored out a 6 from each of these terms, just to get rid of all your denominators here, so let's factor out a 6, because that's the least common denominator between 3, 2, and 1. Okay? Now, if you factored out a 6, that gives you 2a over 6, 3b over 6, and 6c. Okay, we've already gotten rid of these, so let's get those out of there so we don't confuse them. Okay, now That gives you your b over a over 6. Okay, what do we have left? Okay, I do need the things I've erased. I'm sorry about that. Okay, well, let's see what we've got left. 2a times b squared okay, I do need those polynomials I erased before. I'm going to just advise you to take a look at the book, okay? And you'll see there they factor out the b minus a over 6, and that left them with, and I guess I can go on and do this. I'd started to do it and I just quit. It's 2 times capital A times b squared plus ab plus a squared, okay, plus 3b, we already factored out the 6, so it's 3b times b plus a plus 6c. Okay. All right. Now, yeah. Now, this is the part I was dreading. So I think what I'm going to do now is erase that middle line again because we've already used it. And I think I'll erase the bottom too because we've already used that. Okay. So here's our b, oops. Gotta get the pen back. Okay. There's the b minus a over 6. Okay. Now what do we have left over? And I'm going to go on and write back in here what this was. This is a b cubed over 3 plus b squared over 2 plus c b minus a little a cubed over 3 minus b little b squared over 2 minus ca. That's an a here, little a, sorry. Okay, now there's just way too much here to write in what little space I've got. Okay, I just have to let you look at the book because it's way too much for me to do it on the page where you can see everything. It does come out this way. Here's what they're asking you to remember. The integral of a quadratic is b minus a over 6. We see where that comes from. Okay. Now, times that integral at the lower limit plus 4 times the integral of the average of the two, okay, the polynomial evaluated at the average of the two, plus b at the upper limit, you know, the polynomial evaluated at the upper limit. Okay, they don't go into how you do it, they just say there it is. Okay, they do show you in the book, but they kind of leave you hanging here. okay? And they skip so many steps, it's really hard to follow, okay? So let's move on from there and let's see what they're saying. To develop Simpson's rule for approximating a definite integral, you again partition the interval a to b into n subintervals, just like we've done before, each of width delta x is b minus a over n, just like we have always you did with the trapezoid. This time, however, n is required to be even. We didn't require that before. The two examples we gave was n was 4 and 8. They happen to be even. But this one, you have to have the n being an even number. Okay? And there's a reason for it. We'll see that. And the subintervals are grouped in pairs such that, here's what you do. A is your first one, x sub 0. And then you have x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, okay, and all the way up. And the x sub n has to be b, okay? Now, your subintervals now are x0 to x2, x2 to x4, x4 to x6, x6 to x8, xn minus 2 up to x sub n. There's 3 in every one. This one's doubled, okay? Let's think about this. You use this one once and that one once, a lot like we did with the trapezoid rule. We have this one here, okay, but then you have this one used twice, this one used twice, but okay. On each double interval, x sub I minus 2 to x sub I, you can approximate f by a polynomial p of degree less than or equal to 2. Now we're usually going to use 2, okay? But when you're doing that, you get, from back that we had before, see if they show this. For example, in this subinterval 0 to 2, x sub 0 to x sub 2, choose the polynomial of least degree passing through the points x0, y0, x1, y1, and x2, y2. So you've got x0, y0, x1, y1, and x2, y2. That's the first integral here. Now, we're going to do that, okay? So we're going to use this point once. Then we'll go to the next one, slide over 1, and x sub 1, 1, x sub 2, 2, and x sub 3, 3. So you're going to use that one once again, so that'll make twice here, once again here, that's twice there, and once again here. Okay, and that's just the first time for that point. So we keep doing this, okay, and using p as an approximation to f on subinterval, you have, remember that we said before was x2 minus x0 over 6. Then you have the p of x0, which you're only going to use once, okay, 4 of these, of the average one, and then p of x2 you're going to use once. Okay, I misstated before. Then the next subinterval, you'll use this one again, so that would be twice, and then you use this again. But now this, remember, is a 4 here and a 2 there. Okay, so these are going to cancel out and be just 2. I hadn't noticed that before. Yeah, I don't know why they did that. Well, they're showing that it's a minus b over 2, but then it's 4 times that. So this could be divided into that and do 2 of those. Okay? All right. So you have the first subinterval using once, the first point once. This one you're going to use twice, the one in the middle, and then the third one you'll use once here. Okay? And when you do that, this is using this once, that twice, that once. But then you use this once again, that twice, and that once. Okay? and then this once, that twice, and that once. So you're doing, you're doubling up in the middle. Okay, this is hard to show on so many different screens here. Okay, so boy, this gets so confusing here. The wow, the x of 2 minus x of 1, you have to go back here. They're not showing that, are they? Okay. They're just flying it into, oh, here, yeah. That this is x2 minus x1 is twice b minus a over n, okay? That's your subinterval there. You've got two of them for every one, so that's why they put the 2 there. The over 6 came from up here. And then here's your piece of 0. Okay, now this is going back to the earlier form. Okay, sorry about this. Back here, if you're using P of A and P of B, this is now P of x0 and P of x2. This would be P of x1. That's exactly halfway between those two. Okay, so it's 4 of those. So P of A once, 4 of P of 1, and P of 2. And then the next one's going to use a P of 2 again, so it'd be twice of those, 4P of that next one, okay, plus another P of C. So what happens here is this. Your first one you use once, and then you use 4 times that one, twice this one because you're going to come back and use that for the next one, 4 times the next one, plus twice the next one, all the way up until you finally get to your repeating this procedure over the entire interval a to b produces this theorem. Let's go to the theorem. Let f be continuous on a to b. Let n be an even integer. Remember, with Simpson's rule, that number of intervals has to be even. Simpson's rule then for approximating that function is b minus a over 3n. Okay? Remember the trapezoid rule was b minus a over 2n. This is b minus a over 3n. Oops, too far. B minus a over 3n times the first one once, but then the second interval, f of x of 1, 4 times, the next one twice, then 4, then twice, then 4, then twice, all the way up until your third from the end is going to be twice, 4, and that last one only once. Okay? That's because you only use the endpoints once each. The intermediate endpoints you use once for this interval and once for that interval, so it's twice, and the one in between those two is always 4 times. Okay? Seems bizarre, but it's true. Okay? Moreover, as n approaches infinity, the right-hand side approaches that same function we started with. How are we doing on time? Oh man, we've run out of time. I'm sorry. Shouldn't have even tried to show how they got their numbers, and I did too much talking at the beginning at the same time. So here we're going to be doing, we've just done Simpson's rule, we're going to be starting with example 2. I'm sorry I took too much time talking, but what we can do so far, and we almost finished H6, believe it or not, okay? You can do any of the odds, 3 through 13. using trapezoid rule. Okay, you don't need to do Simpson's rule. You do any of the odds 15 through 23, again, only doing trapezoid rule, not Simpson's rule. Okay, and stop there. We'll pick up the rest of those next time. Any questions? Sorry I took too much time at the beginning talking about the procedure. So you decide, folks, are you going to go to campus and register for spring? If you do, please do, okay? But you can also sign up for virtual advising and then sign up yourself, and you don't have to go and get exposed. Okay. Now, I think maybe part of Ashton's, I believe it was, comments earlier, and I don't mean to sound negative on this. In fact, I really don't want to sound negative on this. What you have to do, folks, if you want to take Cal 3 in the spring, it's on the schedule, but it doesn't have an instructor listed. At least I think it's still on the schedule. I put it on the schedule. And if they get enough students to sign up for it, they're going to have to find an instructor for it. But right now, it's listed as staff, I guess, or I don't know how they do it under this new system. It may just say to be announced as the instructor or something. In the old thing, we always called it staff if we didn't have an instructor to put there. Sign up for it, folks. Please do. It could be plenty of others are needing the Cal 3 also in the spring, and then they will find an instructor for it. It just won't be me, okay? And when you get into that class, whoever the instructor is, you let them know where we ended, because we've had 3 really bad terms, okay? When did y'all start Cal 1? In the summer? In the summer, we had a shortened term, and it was also there were holidays that messed up our completion of things in the summer. This term, again, holidays have messed us up because we lost both Labor Day and Veterans Day. So we lost an entire week this term as well. So whoever you get for Cal 3, if you get Cal 3, and I hope you do, then let them know where we ended off this time, and that's where they'll begin Cal 3, and they'll decide how to wrap it up. The Cal 3 group now that's coming up in just about half an hour, they were even in worse shape because last spring was the term we had to leave campus, so we had a very disruptive spring term. We got behind, and then summer we tried to catch up as much as possible, but again, we had the same issue with a shortened term and holidays messed us up there too, and then this term they're in the same boat, so they're not going to get as much Cal 3 done as you'll be able to get done. But this 2020 has been a terrible year to try to teach because there's been so many disruptions. So anyway, any questions? I shouldn't have gotten off onto that either, but I did want to let you know. Any questions? Okay, I'm trying to get the thing to stop sharing. There we go. And we will see you on Wednesday, and we'll pick up and go from here. And of course, you know, next week is what? Thanksgiving week. And there are no classes at all during Thanksgiving week. We have meetings Monday, Tuesday, and Wednesday, but no classes next week. Then on Thursday and Friday, the schools close completely. So the schools open Monday, Tuesday, and Wednesday of next week. There shouldn't be many students there, so if you do need to come in and take care of some business, that should be a fairly safe time. And then if you do need to, just go and take care of issues then. And then we come back for one more week after Thanksgiving, and then it's final exams week. So on the Wednesday before after Thanksgiving, the Wednesday after Thanksgiving, I'll be giving you your final test. That'll be your final exam, and that will go from there. Okay? Any questions? Good deal. Sorry we went over, but there'll be no extra charge. Okay? Take care. We'll see you Wednesday. Bye bye.